That's a saddle point function. So this Hessian matrix, it quickly can help you. You know, taking a second order derivation is not hard. You can code it easily, right? By doing so, you can quickly do eigenvalue decomposition and decide, should you minimize, should you maximize? Because if it's convex, you know you need to minimize that. It's concave, you need to maximize this problem, right? If it's saddle point, that means some part of it is minimization, some part of it is maximization. Does that make sense then? Okay, so any question before I move on?
Excuse me, does the order matters in for Hessian method? Because
Which order you talking?
or order of derivatives. Like for example, let's say derivative of f in the end row on the first column. So we take the derivative of f.
Yes, we take through in order.
In order.
Yeah. So now we are done with algebra. So these are the things that I want you to, more than the statistic part, these are the things I want to memorize. Seriously, if you cannot learn it, memorize it, because we're just going to use it, you know. But by practice, when we constantly taking this derivation, constantly saying that this is convex because of that, this is, you automatically going to learn it, you know, and getting better in it. But review this chapter now.
So if it's zero, if the eigenvalue is zero, what do we do? We don't minimize the maximum.
So that tells you that that when you have a problem, imagine I have a problem that some part of it is maximization, some part of it is minimization, right? So this could mean two things. You either have two functions like that, you can break down your function, you know, or basically you need to solve it using some suboptimal basically problems or suboptimal optimization. It doesn't go under the same umbrella over there, you know. It happens. I personally haven't worked with any experience, any example that goes into that umbrella, but it happens. We have suboptimal, sub-problem optimization techniques that, you know, you solve for one part versus sub part, and then you solve for the second part. So you basically divide the problem into two sections. So now we're going to start the first chapter here called regression. Now, think about this. So whenever we are moving forward, whenever I want to teach a concept, a chapter, I don't like to just write it on the board. That doesn't make sense. You get tired, I also get tired. Same same thing is when I code. I don't want to come over here and just code so you can just take the code, you know. So I can just give you the code, right? So whenever I want to teach a chapter, I want you to just understand the steps that I'm taking. I try to give you basically, I'm trying to not only teach you the algorithm, give you the mindset of how, if I see a data, a problem, how should I decide which approach should I go for it, you know? So just basically try to follow. You will see there's a trajectory, there's steps that I always take for each chapter. They are the same because I want you to basically try to think that way. Now, first thing is that we want to talk about the regression. Okay, so before we write down, okay, what is a regression? You know, regression basically is any problem that you receive as input. You know, input could be matrix or input could be vector, right? And you produce one number, right? That becomes regression. So by default, we know that, okay, we have x, which is a set of x is a vector, right? So we have a vector x that has d dimension. That means I have d columns, okay? Now, and I have y, okay? It's the target, okay? Target. Target means that's something that you want to learn to predict. Okay, so I want to learn to predict x to y, right? And I know y is a real number because it's regression. So y is real number. Now, because all I think about is that, okay, I have a vector. So when we talk about regression, we have different type of regression: linear regression, nonlinear regression, polynomial regression, this type of regression, right? For basic, we assume for the moment we're talking about linear regression. Okay, we're assuming linearity. So when I have a data, this data set, and my job is to model it. I know if I get this input, I should be able to predict that target. Okay, and I'm like, okay, this is a real number, so this is a regression problem. I'm not going to jump at the first time and say that, oh, this is non-linear regression. No, I would say that let's go easy. Always let's go easy, right? Let's do linear regression. So how could I map x to y? So if x is the following vector, xt, right? I need to learn some parameters, right? Because each vector, each x is one column, right? For each column, you are going to learn one weight or parameter. We're going to, moving forward, show that as theta. Theta, sometimes you might see w, theta or w. Anytime you see it means parameter, something that you need to learn. Okay, is not given. Is that unknown? Basically, value. We have d of them because you have d columns. You have d parameters. Unknown. You don't know it. We are assuming that. Okay, I want to map x to y using theta. Okay, so what is my goal? My goal is that, or my hypothesis H, to get x as an input, considering set of parameters, and predict y. That's what I want to do. Okay, I want to have, this is a hypothesis, not a model. My hypothesis is that I can map x to y. Okay. Okay, I want to map x to y. But how can I do that? Like, how could we formulate this problem? You need to think about this. X goes to y. Will x exactly give me y? No, you don't get precise answer. Even if your model is perfect, you will still have some error. Even your error could be 0.0 something, right? So this is not technically, theoretically possible. So what you get basically is that h theta x gives you y hat or y tilde or whatever. So if in the other class we saw y tilde, these are the same thing. So like depending on what I use. So that's technically what you predict. That's what you want, right? If that doesn't make sense, think about it this way. The perfect scenario model is also will have error. It's never going to give you perfectly the answer. Even in a classification that you want to predict, what is the probability? This is a student versus a chair. The model doesn't tell you that he's a student. It will tell you 99.99% is a student, 0.00% is a chair. You see, it's not a perfect answer, right? Doesn't matter what algorithm we are using. Now, okay, we want to do this mapping. Now, you need to think about, okay, if I want to map this, how could I train it? How could I do that? Okay. So anytime you want to train something, train means to teach the model, right? You need to think about the pipeline. What's that pipeline? Data, you know, there is a data, right? There is a model. There's a data that goes to the model. And model predicts basically y hat, correct? So that's it. Did I learn? No, because the weight of this model could be random. So you need to create a pipeline. What's that pipeline? You need to have a loop. This loop comes from here. So you will say that if my model predicts this, I need to compare that with actual expected value. We call this J, we will talk about it. Okay. J receives this and receives that and calculate how much error you have. Okay. That error comes back, loop goes back to your model. And this process will repeat. At some point here, we have an if statement. Okay. We will say that if J is too small, stop. If the error that I'm seeing is too small, that means I have learned. Stop this loop. Okay. So we are going to look at this problem in this scenario. The majority of problems are going to be like that. Data model, some basically function that calculates the error, looping back. That becomes the learning part. Okay. So we want to map X to Y hat. What do I need? Okay, I have a model. What's a model? No, sorry, I don't have a model. I want a model. What's a model? We say it's linear regression. That's theta, that's X. I have two vectors. I want those two vectors to produce me a number. What would come to your mind? External question. Yeah, dot product, inner product, right? So I can, rather than, basically I can say H theta X equal theta minus X. The inner product of these two vectors gives me a number, right? So you see, we were thinking about what model I can use because it's two vector. I already know that two vector, if you do inner product, it gives you a basically element-wise multiplication, which is element-wise multiplication, which is a linear regression, right? So this gives you I have. Now I have a model. What do I need? J. Okay, what is J now? Let's go. So in case of regression, we have Y and we have this Y hat or Y, it's Y tilde or Y. It's a real number, right? If I ask you that, give me one function that tells you how much is your error, what comes to your mind? Yeah, simple, right? Y minus, what else? Y minus Y hat to the power of 2, right? Absolute value of Y minus Y hat. The square root of this. We have all of those functions. You have probably heard of those, right? So any function that you basically tells you that how much is difference between these two value, predicted value, we call it loss function. Okay. Any function that tells you the difference between these two is a loss function. But that's not J. That's between one basically data point. J is called cost function. Is the summation over all data points. Loss function is for one data point. Cost function becomes this basically summation of all the errors. I put L here because you can use any L, any loss function. I just leave L. It's fine. You decide what you want to use. But when you hear the term loss function versus cost function, remember this: loss function is for one, cost function is for all, or an average. Okay. So now, okay, I have a cost function which sums over all the loss functions. Now, Now we have up to this point. We want to talk about this loop. Okay, this learning. How do we learn? What's the goal? Okay, the goal is to minimize this J, right? So my goal is to minimize this J. Okay. Now, what we do basically, we will say this is J of theta. Cost function for theta, because theta is the parameter that you are learning. Okay. Your goal is to minimize this. That's the goal. But technically, by minimizing that, what will you find? What's the end goal that you have in this algorithm? To find what?
No error.
But after that, what do you find? Thetas. The end goal is to find theta. How do we achieve that? Basically by minimizing the error, right? So we formulate that somehow because the end goal should be to get theta. So we formulate that this way. We will say best possible theta, theta star. You know, that's what you want to learn. Is a theta that arg mean, I'm going to go over what's arg mean, is value. Okay. We want to minimize this, but best theta is a theta that arg mean that. I'm going to tell you what's arg mean. So I have theta 1, which gives me 2, 4, 6. I had 3 columns. Okay. And next time I find theta 2 is 1.8, 3.4, 7.2, and so on. Every time I solve in each learning, I get a new theta. Okay. And my goal is to minimize this. When I say, and I know end goal after minimizing that is to figure out which one of these theta I should pick. So in order to formulate that, we will say that the best theta between all those theta is a theta that if you replace it into J, gives you the minimum value. That function called arg mean. If you have a bunch of variables and you want to say that which one of them give me the minimum answer, you use arg mean. If you use mean tells you, only gives you the minimum answer, doesn't tell you which one gave you the minimum answer. Does that make sense? Arg mean. Another one we have is arg max. Anytime you're doing a maximization, you use arg max. Which one is maximizing that for me? You use this whenever you have so many that you want to select from. Okay, that's arg max and arg mean.
So could you repeat arg min once again?
Yeah. So when we are starting here, I have this data. Okay. We will see that majority of the algorithms that we have, they are not closed form solution. That means you need to learn iteratively. So first time I have this data, and I want to learn this model. I know I formulate the model looks like this. Okay. But what is theta? First iteration, your model doesn't know what's theta. What we do, which we will see, randomly assign some theta. All your theta 0, all your theta 0.1, or whatever, randomly. So I have a vector randomly generated, theta 0. And let's say they are all 1. First step. I multiply that vector as this way by in each data point in this data. For each data point, that gives me one predicted value. I compare the predicted value with actual value. Calculate the J, right? Then I update the theta. I will tell you that how later on you update. Then from this, we went to theta 1. I passed the theta 1 to the model. Calculate the error. Go back. Should I stop? No. Continue. I update theta, go to theta 2. And I repeat this process. At some point, your model stops. You have one last theta, theta n. Let's say is 2, 4, 6.4. Okay. But should you use that one? Does it mean the best one? So in order to decide which one is the best, you look back and say that across all this theta, which theta, if I replace it into my model, gives me the best or the minimum error. Okay, that function, that which, in coding, if I say NP, where, in NumPy, if you guys work with NumPy, it's an NP where, and you pass a vector, it's an NP where 1, 2, let's say I have this vector, I will ask this NumPy, NP where 3. I will ask this function, which element in this vector is 3? It will return me this location. It says element 0, 1, 2. It doesn't tell me 3, it tells me element 2. Right? In this scenario, basically, all I'm saying, this function says that I want to minimize, but tell me which one minimizing it for me. It returns you the theta that minimizing. If you use mean, it only replaces the theta, all these thetas, back to the function, and it only gives you the minimum error. Like your minimum error is 22, but it doesn't tell you that, okay, what's your theta? Which theta gives you the minimum error? That's the argument. Is that clear?
Will we define the error, like how much is acceptable and they can?
We will get to that part. We will get to that. Yes.
So that all everything makes sense. I'm just curious because we're saying that the loop is saying if J is too small, stop. But we're not saying that the last set of thetas are the minimum, where the minimum would occur.
So we're going to get to that soon. Not always you stop because you reach to a condition. You know, there are caveats. It's why when we look through this loop, not every time you use all your data. You use sample parameter. You're going to talk. So at the end, you need to check that parameter with respect to total data. Right? We're going to talk about it right now. So just bear with me. So now we say that, okay, we want to find the theta that minimizes argument theta. Yeah. You know this theta that I write under argument, basically that tells you that you are solving this with respect to this. If I had theta and b, it tells you that you solve this with respect to these two. So you will write the parameters under. Okay. J of theta. Now, let's go to J of theta. So I wrote J of theta at this point, right? Summation of bunch of losses, right? Now, let's define, in order to be able to solve this problem, I'm going to use one basically loss function. So let's say L of y and y hat is basically y minus y hat to the power of 2. Or actually, y hat minus predicted. Doesn't matter, it's a square root, right? So we're going to use basically a square error. So this is called a square error for L. So when we say J of theta, we say this is summation of this, right? All the square errors. Now, what is y hat? You know y hat is theta transpose xi. So this should be a I, sorry, because I put. Anyway, it's a summation, there should be some I. This is minus yi to the power of 2. Correct? So because y hat we know by default was we define it as theta transpose x, right? That's linear regression. Now, Okay, so look at the dimension. The inner product is a scalar, right? And this is also a scalar, it gives you a scalar, summation of lots of the scalar, right? Now, I told you the majority of time, you want to learn how to convert this into a matrix form. Write it as a matrix multiplication rather than, formula. And now, if we want to do this, summation of some errors squared, right? The best way to do that, the best way to do that is going to be x theta minus y norm to a square. Now let's see why. First thing you notice that x theta rather than theta transpose x. Okay. Why that happened? What you see here, theta transpose x, is for one vector multiplication. When you want to convert it into a matrix multiplication, you need to swap. Do that. Think about the dimension. How many data points I have? N. What should be the size of how many errors should I get? N. Right? So x is n by d, right? Theta is d by 1, right? If you say theta times x, doesn't add up, right? You basically, I told you would learn when to decide which side to put basically the vectors or matrices as one example. I know this multiplication should produce n values. How will that happen? If I put x first and theta after, right? This times that produces y hat, which is n by 1. N by 1 minus y, which is n by 1 to the power of 2, right? So now, if we have that here, so that basically we are saying that so let's say two ways you can represent this. One day you can say that theta transpose x1 y 2. Okay. Or you can say basically A1 transpose A n theta minus y1, right? So either way, this times that basically this one will get another transpose if you use it that way, because you need to upward it. But this one basically becomes this times that A1 transpose this becomes the inner x1, sorry. X1 transpose gives you the predicted value, so this becomes x1 transpose theta on xn transpose theta and theta theta, right? Because theta has a dimension minus y1 all the way to yn norm 2. Okay, a scalar minus a scalar. Scalar minus a scalar. What's the dimension? You get that in here. Norm 2 of basically n by 1 vector, correct? Okay, let's write this somewhere cleaner. Does this part make sense? Which part? Does this part make sense or no? So does this make sense? So I'm just writing this to proving why it works. So x times theta minus y. I'm going to present x as a row matrix. x1 transpose through xn transpose, correct? Each row, how many dimensions it has? D dimension, right? D columns, because we have 1, 2, 3. Times theta. Theta is one vector. I leave it as theta. What's the dimension of theta?
D times 1.
D times 1. D columns. Always theta is with respect to columns. Minus the output. Sorry, expected value or target. So do this multiplication. There's going to be x1 transpose theta. And it's going to be a one vector, right? Xn transpose theta. So you have one vector minus this vector. You get another vector, right? You're calculating the norm to the square of that vector. What's the definition of norm 2? Summation of the square values. Because you have it to the power of 2, you get rid of the square root. Right? So this basically means summation of x1 transpose minus y1 to the power of 2. Isn't that the same thing? Right? So I just try to tell you that this exactly gives you the same answer. This is individual, but this is in a matrix form. And we use matrix for the majority of basically algorithms here. So, okay, now we reach to optimal theta is a theta that minimizes x theta minus y. Because rather than j of theta, we are going to use this term, right? So that's the goal, to find the best theta where the theta that minimizes the cost function. This was the cost function. This was the loss function. Cost function was summation of all loss function. This term, we wrote it as this term. We just picked that, put it back here. So that's what we have, right? Does that make sense? So, my goal is to minimize this. Okay, now. So let's talk about convex functions. So we're coming to here. Because my goal is to minimize that function. That's a function, x transpose minus y. But how do I know it's convex? How do I know I can basically minimize it? So first then, actually what is a convex function? That's a definition. Now, we will say that any function f, okay, as a series of basically vector produce a number. Any function f that receive a vector theta. Could be anything, but just use theta. Where or that's right, if any function is convex if and only if for any alpha between range 0 and 1. Okay. And for a theta 1 and a theta 2, okay, you get the following. F of alpha theta 1 plus 1 minus alpha theta 2, triangular inequality, less than equal alpha f of theta 1 plus 1 minus alpha of theta 2. Okay. So any function that the following property holds is convex. I know it looks basically complicated, but we just simplify. What does it tell me? there's a function, gets a vector, gives you a number. Okay, I'm telling you, if you randomly pick a value, a number between 0 and 1, any number between 0 and 1, okay, and pick 2 thetas. Theta is what you feed to that function, 2 random theta, okay. This function, this value, should be always less than this value. No, that didn't make it simplify. That didn't simplify, but let's look at it. Let's assume we have a function f of theta or j of theta in this point. And let's assume it gets 1 theta as input, not a vector, it's just one theta. And I say that a convex function looks like this, right? So, first thing is that let's pick an alpha, basically alpha. So let's say alpha is 0.4 randomly. Okay. And I'm going to pick 2 theta from this axis randomly. Okay. Let's say theta 2, theta 1. Anywhere on this basically axis, you can pick 2 thetas. Let's see what does that equation tell you then. Multiply alpha by theta 1 plus 1 minus alpha times theta 2. Okay, that means 0.4 theta 1 plus 0.6 theta 2. That should be a number, right? In this example. Where do you think that number will fall? Always between theta 1 and theta 2. Right? Always will fall somewhere here. Okay. Let's say this is falling here. So we call this theta 3. Right? So let's say this is theta 3. What does the equation tell you? The equation tells you that f of theta 3, right, is less than equal 0.4 f of theta 1 plus 0.46 f of theta 2. Now, what does this remind you of? That equation, what does that remind you of? No, just that last equation. Number times a function plus another number times a line. That's the equation of a line. A times x plus b times y. Right? So this is the equation of the line. What does that mean? That means this is theta 2. Find the corresponding f of theta. This is theta 1. Find the corresponding f of theta 1. This is f of theta 1. This is f of theta 2. How do we find it? Just map it, right? Connect them with the line together. That's the equation of that line. Okay. So what does that property tell you, formula? For any theta 3 that falls between theta 2 and theta 1, the corresponding f of theta 3 is always below that line, less than the line connecting these 2 points together. Any function that this holds, it's called convex function. Again, lame language. Any function that if you pick 2 random data points on this function, okay, 2 random data points, and connect the corresponding points for those data points with the line together, okay, any other data point that is between those theta 1 and theta 2 will have a f value below the line. Now, look at this example. Do you think this is convex or not?
It's not, but actually
What's that?
multiple convexity.
Well, yeah, let's stick with one.
It's not.
Why not?
Because of that point in the middle.
So right, so if you pick this one, and this one, which are 2 points, 2 thetas. Connect them with the line. This is above the line. Anytime you have a function, connect the line. You shouldn't have a point that passes the line. If it passes the line, it's not convex. Always, any 2 point, doesn't matter. Now let's look at this, for example. Is this convex?
No.
It's convex.
Yes, it's convex. Because it says less than equal. I pick this 2 on the line. Any point on the line is also equal. So always think that when you want to understand convex, there are 2 ways. One is that visualize the function. How you have the shape of a function. If you have that, it's really easy. You can basically draw a line, make a decision if it's convex or not. But now the question is that how should I find the shape of a function? Like, let's say one way is that on paper, if you want to draw it, you make a sample, maybe you sample from data. Like I have a function, let's say the function says f of x equal x1 plus 5x2. I want to see what's the shape of this. So I first find what's the range x1 and x2 can get, minimum to maximum. Then you sample, right? If you want to code it, you basically pick from the minimum value through the maximum value. You pass it to the function. It gives you the f for that. Now you have, when you find the f's, you put them as a point, it looks like this. You connect them together, that becomes the shape of the function, right? That's one way. So if you could draw the shape of the function, then you can decide if it's convex or not. Not always you can do that, it's not that feasible. So the analytical solution is to take a second order derivation, or basically that Hessian, the gradient of the function. You take 2 derivation or a gradient, and if it's positive semi-definite, it's convex. Okay, so take 2 derivation right now. So take 2 derivation of f of theta with respect to theta, and if it's always greater than equal to the in positive semi-definite, then it's convex. So you see the connections. You need to try to basically remember this Hessian gradients when you are positive definite, when you are positive semi-definite, and it's not only for this class. Trust me, you will use this. You're working somewhere, you are working, any of you have already done internship or co-op something, right? Yes. So have you done whiteboarding in your co-op? Right, you see, so when you define a problem, like you have a goal, you have a data set, you're like, we want to solve this, we have 3 months, or some companies it's called agile, you have a short time. And you do whiteboarding, so you go write down the whole process and say that, okay, this is the process, we want to minimize this, we want to solve it. Then you or someone else might be responsible to go look at the function, sees that, hey, can we minimize this? Can we maximize this? Then this type of thing will become handy, right? If you have some idea, you write down the cost function, you go to a couple of derivation. If it's convex, you can say, yes, we can minimize it. If it's convex, that means you can multiply by negative and maximize it also. Right? Because the minimum, the negative of convex becomes the concave. So there's some relationship that you can learn. So we're going to stop here.
In the first